So we're back. We're going to be talking about dynamics now. We have identified a few convenient models for physical systems. Many more complicated systems can be mapped to these simple models. And as you'll see, whether you like it or not, that's what very many people do. All right, we use simplified And the question that we want to ask is this something that we could write kind of like an exponential? Right? This kind of looks like an exponential. It looks like a term with, the first term, of course, is 1. And remind ourselves what exponential is. E to the x is x to the n over n factorial. Sum on n equals 1. In this case, actually 0 to infinity. This would be all the terms from 1 up, and this is the term 0. So if one term is like the integral, and the other one you plug it in, it's like the integral squared, and the integral squared, and so on. That means squaring means do the integral again and again. So the question is this actually an exponential? Okay, but thinking about this as if it was an exponential, immediately recognize that the upper limits of each of the integrals are not the same. So it's not likely that this is actually going to work. But there is an analogy to an exponential function. And so you'll see later on, when we see this series, we're actually going to use a term that is time-ordered exponential operator. All right, so there's two things we need to see. First is how these limits work. Notice it's t naught to tau 2. The next one would be from t naught up to tau 3 and so on, which is not the same thing as going from t naught to t and t naught to t and t naught to t and t naught to t, which is what you would need to do if you wanted to plug it back in and call it that. All right. An analogy, the way to think about that is if we're integrating over this region, we might think, oh, if I'm integrating t1 or tau 1 from 0 to t, then I'm integrating it from t naught to t, and tau 2 from t naught up to t, right? Then I'll be integrating the function over this whole region. Instead, what we're doing is we're integrating from tau 1 up to tau 2, so there's a smaller region of this where that's the case. This is tau 2. So we're integrating tau 1 from t naught up to whatever t2 or tau 2 happens to be, which corresponds to this region here. All right, and that region is obviously half of that one. Well, if it was just a matter of half, that wouldn't be so bad. Of course, we don't know what the function is doing on this area. So that's number one. The integral limits aren't all the same. The second thing is that we need to keep the ordering of the operators perfectly correct. Why is that? Because there's no guarantee that the Hamiltonian at time tau n, or let's make it more generic than that, not just the last time. There's no guarantee that the Hamiltonian at any two times, tau j, commutes with the Hamiltonian at tau k. This is not necessarily equal to 0. Therefore, the ordering of the operators matters. We can't change their ordering since they don't commute. All right. Nevertheless, because this looks similar to an exponential, we're going to use the notation tau ut t naught is equal to e, and then we put a subscript of a plus sign here, minus I over h bar with this integral, t naught up to t, d tau h tau. All right, and what we call this thing here a time-ordered exponential operator. And we shouldn't think of this as literally this function. We think of this as this series that's summed. Okay, so that's a little tiny bit of notation. All right, and so what we're going to do now is we're going to work out what are the steps we need to do to break up the time evolution into a part that we can keep completely intact and a part that we treat with a series that we truncate, and that will be the basis for time-dependent perturbation theory. So let's start that now. It's actually very straightforward. We're going to simply postulate, and it's very general, that the Hamiltonian can be written as a sum of two terms. This is completely general. There's nothing here that says H naught has to be known, and there's nothing that says H prime has to be small. Okay, so this is completely generic. All right, so what we're going to do then is we're going to simply define a few things. All right, the first thing that we're going to do is we're going to define a time evolution operator that's specific to the H naught part of the Hamiltonian, right? We're going to call that U naught. So U of T naught is going to be defined this way, as the time evolution operator that arises from the H naught Hamiltonian. So clearly you can't get the full evolution of the quantum system if you only have part of it. But nevertheless, you can always imagine defining a time evolution operator that is due to just the H naught part of the Hamiltonian. Okay, so that's step one. The next thing that we're going to do is we're going to define an intermediate picture. Remember before we had the Schrodinger picture? So Schrodinger picture has the time evolving states and nominally time independent operators. Now, of course, the operator could be an oscillating field, and of course, then it would also have some time evolution. And the Heisenberg picture is the time evolving operators and time independent states. And we arrived at this just by writing down an expectation value of an operator and then realizing we could put the parentheses in different spots, and that's what gave us the two different pictures. Now what we're going to do is we're going to think a little bit differently about this, and we're going to define the Schrodinger picture state in this way. And we're going to define it, essentially what we're doing is we're defining the interaction picture state, but we're defining it in this sort of this direction. You could have defined it in the other direction if you wanted to. You'll see what I mean by direction in a minute. So it's customary, or you'll see in the notes I'm taking this sort of derivation from, by the way, are from the Mukamel book, which you can find the notes from the chapter from that. It's either, I think it's chapter 3. It's either 3 or 4. The two sort of quantum background chapters of Mukamel's book on nonlinear optics, nonlinear spectroscopy. But it follows the same in pretty much any quantum textbook that does this. So I can always just write this. Remember, U is a unitary operator, which means the inverse is equal to the adjoint. So I can rewrite this in this different direction. I can write it as psi I is equal to U inverse, or U dagger, same thing, U naught, T naught, psi S. If you multiply this upper equation, sorry if this is more steps than I would normally do at one. If you multiply this by U naught dagger, then the U naught dagger comes across. U naught dagger is equal to U naught inverse because it's unitary operator. So that makes with U naught 1 the identity operator, and you get UI psi I. So that's the same thing as just writing it like this. So you can see it either way. All right, and so what we're going to do now is we're going to take the Schrodinger picture, the standard Schrodinger picture that we always have, Schrodinger equation. So we'll have psi S, right? The time derivative of that, of course, is minus I over H bar, H of T psi S. Okay, and what we're going to do is we're going to substitute in this definition, or this other way of writing things, into here, right? So we take this piece and we put it in here, and here, of course. So we'll have the time derivative of U naught psi I is equal to minus I over h bar, h u naught psi I. All right, so let's just do the derivative on the left-hand side. So remember, this is a pretty standard thing. There's going to be two terms. You're going to have the derivative of u naught and the derivative of psi I. The derivative of u naught we know, because we just sort of postulated that that would be this, right? And then that'll give us, and then we'll have the derivative of psi I. Once we have this, we'll move it over to the other side, and we'll see that we can write an equation of motion, or the, if you will, the Schrodinger equation, for the interaction picture state vector. So let's do those steps out. But hopefully it's reasonably clear what the roadmap of this is. So the first term we're going to have is the derivative of u naught. All right. I'll leave some of the t's out sometimes when I just want to save a little bit of space. Times psi I plus u naught times the derivative of psi I. This is this. So we have minus I over h bar, h naught of t, u naught, t naught, psi I t, plus u naught times dt psi I of t. And this is just equal to the stuff up here. Nothing's different here. Minus I over h bar, h of t, u naught, psi I. All right. So the next step here that we can do before we have to erase the board is we're going to parentheses the entire equation, right? And we're going to multiply on the left-hand side by u naught dagger, t naught. Let me write that again. That looks bad. Okay, so we're multiplying on the left-hand side by u naught dagger, t naught, same time interval, but u naught. And what do we notice is going to happen? Let's underline the terms that connect. So we have u naught, h naught, u naught dagger, h naught, u naught, operating on psi I. We're going to have u naught times u naught. Sorry, u naught dagger times u naught. That's going to give us a 1 because they're unitary operators, which will then isolate the derivative of psi I all by itself. And on the other side, we're going to have u naught dagger h u naught. Okay? And so what that's going to give us is it's going to give us, all right, and so when u naught dagger operates on h and then u naught, something very interesting is going to happen. What is h? H is the sum of these two terms. Right? So this is going to give us a u naught dagger on one side and a u naught on the other side. All right, so notice that the u naught h, u naught, is there with a minus sign, minus I over h bar, which is exactly the same as the term that we have over here. All right, so that term is going to cancel. Then what's left over is u naught dagger h primed u naught, and that's the thing that's going to be left over, right? So we'll have a name for this, u naught h naught u naught, and that's going to be the interaction picture version of h naught. All right, so I've reproduced that equation up here. Let's underline the different operators that we have. And what we'll notice, of course, is that we have missing constants, minus I over h bar over here. All right, so this bit here, this is the blue pen of cancellation. That term is exactly the same as this term, right? And they go away. We subtract them. I mean, the psi I is this is all operating on the interaction picture vector there. Okay, so when we get rid of those two terms, things actually get quite simple, because now we have the time derivative of psi I is minus I over h bar times u naught dagger h primed of t u naught t naught psi I. All right, and so I said before, I think that u naught dagger of something, u naught is the interaction picture. It would be the interaction picture representation of h naught. We're not using that here, so it ends up canceling out. So instead we have interaction picture for h primed. It's the same. This is the definition of an interaction picture operator. Right? So you can think of that as a definition, 3 bars. All right, so we have a very simple equation then, a Schrodinger equation for psi I minus I over h bar h primed I of t psi I of t. And notice that it only involves the second piece of the Hamiltonian. We already have a way of evolving with respect to the first part by postulating that there is such a time evolution operator, u naught, for the first one. Now we have a way of isolating the second part of the Hamiltonian, and we're going to figure out how do we put all these things together. Okay? So again, this I it refers to the interaction picture. Now, that's a terminology that people use because of the usual application that we have for this. But all we've done really is just separate it up into two pieces, so that's not a big deal. So what we're going to do is just do what we always do, which is to define a time evolution operator in the interaction picture, which is to say if we have a state vector, an interaction picture state vector, then surely we should be able to have an operator that would evolve it from t naught up to t, starting in some initial state. Okay, so this is the sort of the old song here that we've been playing over and over again. You write a Schrodinger equation, you introduce a time evolution operator, you plug the whole state vector into the Schrodinger equation, you transform it to an equation for the operators, which is what we're going to do. And of course, what we're going to see is that the time evolution operator ui is going to look just like the other time evolution operators that we had before. So we're going to be able to write down a time-ordered exponential operator that solves the Schrodinger equation, or the time equation of motion, for the interaction picture time evolution operator. So we'll do that. So we plug it back in. We have this derivative, ui psi I. You can just work this out right now. So it's the derivative of the first and the second. So we'll have the derivative of ui t naught times psi I t naught. And then the second term doesn't have a second term because the time derivative of something that doesn't depend on time is 0. So that's it. So on the right-hand side, we have just what we have. So minus I over h bar. I mean, we don't have to do anything. We just have to substitute. H primed I, ui, this is a function of time, of course, t naught, psi I t naught. All right, and as we've done before, we factor out the psi I of t naught, or another way of saying it, this has to be true for any initial state vector, which gives us back an equation of motion for the interaction picture time evolution operator, which looks just like what you would have expected if you had to just guess it. Okay, so that's that. Now, how do you solve this? You solve this the formal solution, dot, 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 like we just did. And so then you can write down that ui t naught is going to equal the time ordered exponential operator minus I over h bar, t naught to t, d tau, h primed I tau. All right. So we have all of the pieces ready. If you like cooking like I do, then this would be the mise en place. This is getting all of your ingredients chopped up and ready to go, measured out, and now the fun part, putting them all together. All right. So there's a tiny little bit of interesting gymnastics that we have to do with the connection between the Schrodinger picture and the interaction picture. So let me do that up here. All right. All right. So we know that that from the definition of the Schrodinger picture, or the interaction picture, sorry, where this is u naught t naught psi I All right, what we can do now is we can simply plug in to here our postulated, the usual postulated way to have the state at time t in this picture, right? So this is equal to u naught. I'm going to leave out the t's and t naught just to save myself a little bit of room, but everywhere you see a u, make sure you just think in your mind there should be a t and a t naught there, all right? So this is going to be u naught from here, then ui from here, then psi I of t naught. That is important to leave in. Now, what is the difference between the initial state in the Schrodinger picture versus the interaction picture? Nothing's happened yet. So there is no difference. So this is literally equal at t naught. This is exactly the same thing as psi s of t naught. Things only start to diverge after time evolution has occurred. So what we know from that then is that this operator here has to be equal to the full time evolution operator. So that is actually very important. So that we have just proved that u t naught, now I'm putting it all back in because this is the one that you want to save, times ui t naught. So what you get with the interaction picture is the ability to decompose the time evolution operator into a product of two operators, one which derives its entire time dependence from the h naught Hamiltonian, and the other which derives its time dependence from not simply the h primed Hamiltonian, right? Because this is the h primed Hamiltonian in the interaction picture, which means it has a bit of the h naught Hamiltonian sort of wrapped into it because of this transformation. Okay, and so the strategy that we're going to take is we are simply going to keep the full Hamiltonian or the full time evolution operator for u naught, and do the Dyson series for the ui, and then when we chop that at a particular order, we will have our perturbation theory. So there's a few manipulations in that step that are a little bit subtle. And so I want to go through them slowly. And so it's a natural place to stop here before we go and break it up into those pieces. But once we have that, believe it or not, it seems like we haven't made much progress. We're going to literally be able to write down, like 2 boards from now, you know, a calculation of a linear absorption spectrum. It's that simple, right? Now you have to know how to calculate that. But certainly we'll be able to calculate the transition probability from an eigenstate to another eigenstate, provided we have some you know, external influence like a field that's on. We can do that in one board after we finish the tying up of loose ends.